speak about Martingale approach to coalescing random walks. So please.
Okay, thank you very much for this invitation, this opportunity to talk about this joint work with recherches. And yes, I apologize for not being there in person. Okay, I will start introducing the model in our work. We consider a sequence of finite connected graphs. Transitive means that for any two vertices of the graph, there exists an isomorphism on the graph, taking one vertex to the other. Okay, so in particular, for example, the degree of each vertex is constant, it's the same. In this example, we have this graph which is transitive. The degree of each vertex is 3, and for our work, we should consider a sequence of graphs so that the graph are growing. So the graph becomes larger and larger. So keep in mind that the graph is very large. And now on this graph, we place k labeled particles. So these particles will be labeled with the numbers from 1 to k. And we choose the initial positions for these particles. So for this particle 1, we choose a vertex uniformly. For this particle 2, we choose independently a vertex uniform in the graph, and so on. So maybe it's possible that more than one particle is occupying the same vertex in the beginning, but as I said, the size of the graph is going to number of particles is fixed, and so that happens with a very low probability. Okay. For our results, it's the same to consider this initial state, or to consider, for example, just put the particles in k different vertices chosen uniform. It's the same because the graph is very large. Okay, good. We get these particles evolve as a system. That means that each particle performs a continuous time simple random walk on the graph, and the interaction between the particles is that whenever two particles meet, they jump together from the node. A possible path for these dynamics. The state space of these dynamics is, of course, this product of the vertices, k copies of a set of vertices. And for example, suppose that this is my graph. Here we have these 6 particles. They are labeled, as I explained before. And after some time, you see that the particles move. And for example, in this example, the particle 2 and the particle 6 have coalesced. Okay, so from this moment on, they will go together. And then after some time, for example, this particle 4 and this particle 5 have coalesced, and now they are going together. So now we have these 4 groups of particles. Recall that the graph is finite, is connected, and so after some time, you will see just 2 groups of particles. And the final transition will be that you will observe in a finite time that we will see just one group of particles. All the particles have coalesced. Good. As you can see, in a very natural way, these dynamics induce a dynamics on the set of partitions of the numbers from 1 to k. This dynamic, the starting state would be this partition of singletons, yeah, because each particle is occupying just one vertex. And after some time, we'll see a partition like this. This will be the partition. So this will be the partition from the configuration of particles. Of course, we are losing information because for this partition, there are many configuration of particles corresponding to it. Yeah. So the final state for these dynamics would be trigger partition. So here we are using information. In some sense, we are taking a kind of projection, a projection for we are taking a kind of projection from this large state space, which is becoming larger and larger, and here we have this state space, this simplified state space, which is very fixed.
So sorry, Joel, sorry if I interrupt you. Sorry, since the signal is somehow weak, maybe it could be useful if you switch off your video. So you don't, so if you just the video and we follow, okay, your voice and the slides. Okay, thanks. Let us see.
So the goal in this work is now try to find a scaling limit for the projection of these as the size of the graph is going to. Of course, since the graph is becoming larger and larger, then we need to wait a long time to see two particles coalescing. So we need to speed up the process, and this theta is precisely my time scale for this scaling. Okay, let me try to explain a more general problem from which this is an example. So let me try to abstract this problem for a more general set. Okay, so look at this projection. In this projection, we have this very large state space, and this projection induces on this state space a partition. Because, for example, in our model, each partition of the number from 1 to k corresponds to a certain set of positions for the particle, for the k particle. As in our example, we have now a certain Markov process on this large state space. In our example, in our model, it's a projection for this Markov process. This would define dynamics on these and in general, this new dynamics this projection is not Markovian. Just for very special cases, this projection will be Markovian. When the projection of a Markov process is still Markovian, we say that this process is lumpable. Okay, so in our model, that, for example, happens when the graph is the complete graph. I think this is very obvious. No? In the complete graph, we see that the projection will be in fact Markovian. Yeah. Okay, good. So the problem here in this more general setting is trying to state conditions under which this not Markovian process, which is a projection, converges to a Markov process, so that in the limits to recover Markov process. Okay, so we could say that our Markov processes are not lumpable, but in some sense asymptotically lumpable. Yeah. Okay, good. The strategy to approach this problem, we are seeing this in general setting. So again, I have a stable. Okay. So our strategy for approach this problem is, as a first step, to prove guidance for this sequence of processes, for this sequence of projections. And at the second step, we need to characterize the limit point. Okay. So far, this is a very wide strategy in probability, and in the specific Martingale approach, which was introduced by Struck and Barradam, characterize this limiting process, this limit point, as the limit solution of a Martingale problem. So we need to prove that any limit for the limit for any subsequence of these processes converges to a solution for Martingale problem, and we need to prove the uniqueness of this Martingale problem. Okay, so this is the Martingale approach for convergence of processes that Struck and Barrand use for some work. So now in a series of works papers with Professor Claudio Landin, what we try to do is try to use this Martingale approach for the convergence to solve this particular problem of lumping, as I explained here. Okay. Now let me explain very briefly and very roughly speaking the idea behind this approach, or the way in which we try to use this Martingale approach for this lumping problem. Let's fix an arbitrary function f, a real valued function f, on this state space. This is the way in which we are trying to study the evolution of this path, telling you something about this process. Now, recall that this pi t is the projection of Markov process theta t. So you can write this function as a real value function applied to this process theta. Okay, now recall that theta t is in fact Markov process. This is my name here. And so for this Markov process, you have the generator of this Markov process applied to this function. The Martingale, the induced Martingale for our Markov process is eta. The key point in the implementation of the Martingale approach of this expression inside the integral, by this other expression, in which you see that appears this operator, which is applying directly on this, and which is in fact a Martingale. Okay. So when I say that suppose that we may replace this expression by this other expression, I mean that in some way, between these two expressions vanish as a. Okay, so this is, I go back, this is not very precise, but this is what you have to perform. And if we can perform this replacement, then in that line, we will be able to write this expression. Here, the projection of the Markov process eta is precisely our since this is a Martingale. In this case, for any function defined state space, and we could say that pi t is the solution of the Markov. We conclude that pi t is a Markov process we generate.
Okay, so this is the way in which we try to use the Martingale approach introduced by Struck and Barrand in order to solve this problem of lumping. Okay, so here we still are in the general setting. So this is just a very general idea, and I wanted to explain that because I wanted to point out to stress where is the difficult part, the more technical part of this general idea is in fact this replacement. And this is the replacement that you need to prove model by model, and for each model you need different tools. Okay. Okay. So this is the Martingale approach for this problem of lumping. The first model for which with Claudio Landin we succeeded to solve this lumping problem was this model of condensing zero range process. For this model, for this special model, in order to implement this Martingale approach, we use these tools, among other tools, which are the trace process. We need to take a trace of the zero range process. And also we used good estimates of capacities. In that paper, in that model, in our first model, the zero-range process was reversible. So I think that capacities seem to be a very natural and very good tool for that case. But these are the tools that we use for that model. And I would like to stress that our Martingale approach that we use for this lumping problem is not just based on capacities. It's not just an application of capacities, but it's just capacity, a tool we need in that very specific example. So in this sense, I was very happy when I heard about this other model, which is the coalescing random walks, the system of coalescing random walks, because in some sense, this new example is orthogonal to this other example. Here, we cannot use the same tools because it's not natural for this case. We use another tools. And also, I was very happy because also our work about this lumping was very related to the context of metastability. This is considered as an example of metastability, but I think that this coalescing random walks is very well known, and there are some papers about that, and it's not considered in the context of metastability. Okay, good. So now I will return to the problem of the system of coalescing random walks. Let me introduce the Kingman's K-coalescent, which will be finally the limiting process for our problem of lumping. This is a Markov process on this state space, the space of the set of partitions of the numbers from 1 to k. Okay. And in order to define the transition rates for this Markov process, let me introduce this notation. Given two partitions, we will write as this, like this, to say that this partition is obtained from this other partition by merging two blocks. For example, here this is a partition which can be which we obtain from this partition by merging these two blocks, the block 2,6 and the blocks 4,5. And obviously, we introduce the notation because this is the kind of transitions that we expect to see in our limit. Okay, now the Kingman's K-coalescent process is a Markov process starting at this partition of singletons, yeah, and with the rates which are equal to 1 whenever the transition is possible. So in this K-coalescent Kingman's K-coalescent process, we only allow that two group of particles coalesce. It's not allowed that for example, three group of particles can coalesce. Okay, now before stating our results, the result we obtained with Enrique Chavez, these previous results due to Aldous. Aldous consider this parameter of the graph, which is the relaxation time of the graph, which is just the inverse of the spectral gap of a simple random walk on the graph. Okay, and in this result by Aldous from 1989, Aldous considered just two particles. He put these two particles uniformly on the graph. So everything is okay. So in this result, Aldous considered these two particles. He put the particles in uniform way, just as in our model for just two particles. And now he observed the random, the meeting time of these two particles. Okay. So let me call theta the mean value of this meeting time. Recall that they are starting uniformly on the graph. And so Aldous proved that under this condition, I mean, if the relaxation time is of a smaller order than this mean value of the meeting time, then the meeting time of these two particles rescaled at this theta. So this is a result by August. And now, if we consider the result, we can apply the result, for example, for these two particles, for these two, I mean, these two group of particles. And now we could say that the meeting time for each pair of group of particles is converging to exponential distribution. But now the difficulty in order to prove that convergence to a process is in the limit. We see that these meeting times are independent. So this is the main problem here. Okay. Okay. So obviously we use this time for the scaling limit, the mean value of the meeting time, and in our results we can prove that the projection of the coalescing on the work on the steady space on this steady space, the set of partitions, converges to a Kingman K coalescent when you start uniformly and under the same conditions that Albus used in his result. Okay, so if the relaxation time is a smaller order than this meeting time, then we have this limit. Okay, so so I think I can stop here. Thank you very much for your attention.
Thank you.
I suppose that I don't have more time.
Any question? If there are no questions, Michele from the participants.
Yes. Yes, I have a question, just a curiosity. But if you put some probability on the formation of a block, I mean, if two particles meet, have a probability not 0 to not form the block. This model can be studied, or I mean, if two particles meet, then with probability different from 0, they cannot merge.
Okay. Okay. So I think that the main result here is that these meeting times for each couple of groups of particles converges to exponential distribution, and that these exponential and these times are becoming independent in the limit. So if you consider these results, yes, you can change a little the model and say, for example, that if two, I don't know if this is exactly your question, but for example, if two groups of particles meet and they, for example, both disappear or something like that, then you can, yes, you can, I think that we can, actually we are trying to write the precise proof of all these other variations of the model, because we have the core, I believe, we have the main, this main result, which is the independency in the limit of these meeting times.
Okay, other questions? Please, Mika.
No, sorry, no, because this question was motivated by putting some reinforcement. I mean, if two particles meet again next time, they have a higher probability to form a group. I mean, so it can be studied, this model, if you put some reinforcement in the probability to merge two particles or two groups.
Okay. Okay, I'm not sure, but maybe as I have said.
No, just a curiosity, just.
Yes, and I would be interested on all the variations that are relevant in this literature. Right? I'm not a specialist of coalescing, but yes, I would like to prove anything that is relevant in this context.
Okay. Any other question? I have a short question. How strong is your assumption of transitivity? Can you, for instance, do you expect the same behavior on, for instance, random regular graphs with finite degrees?
I believe that you can prove another result in that case, because Aldous proves some things, some results for other graphs. But I'm in our proof it's not possible. So we need to work more effort to prove something like that. It's essentially transitivity for the estimates and for that.
If no further question, thank you very much, Joel.